Okay, today's plan is to go through moments and centers of mass, section 8.3. And then later this week, I'll post supplements on surface area and on probability to wrap up chapter 8. I actually decided against posting a supplement last week. I thought with between the unit exam and all of that, throwing a supplement on top of that was probably not the best approach. I was considering a supplement on moments and centers of mass, but that would probably have pushed probability to today's lecture. And it's very helpful to understand moments and centers of mass before probability. So I didn't think there was a really good way to do that. So I decided to just do moments and centers of mass today, and then have surface area and probability as supplements later this week. And then we'll start differential equations, that section on Wednesday. So that's the plan for this week. DiffEQ I have kind of tentatively slated for 3 class periods, but it's a topic that we offer a full course in DiffEQ, so we can do more on DiffEQ or less on DiffEQ. So that's a topic that can expand or contract based on the time that we have for it. But anyway, so that's the plan for the next week or two. The Unit 1 exam obviously was done last week, so I haven't quite gotten around to grading those yet. There was more than half of the class waited until Sunday to do the exam. I strongly recommend against that. That's taking a pretty big risk with an assessment that's a pretty big chunk of your final course grade. So for future unit exams, I strongly recommend against waiting until the last day. I know that maybe gives you a little more time to study or something, but if something goes wrong, the resources available on, say, a Sunday afternoon or evening are very limited. So, not only do you not have a lot of time to kind of reach out to me or work out a solution, but also just the resources, like, can you go to a library or something and get an internet connection there if your internet's out or something like that. Those are just going to be much more limited on a Sunday evening as opposed to, say, a Friday morning or a Thursday evening or something like that. So just a little thought for future exams. The quote of the day today, I really like, from Nassim Taleb. He was a hedge fund manager. I guess these days he kind of considers himself more of a philosopher. He's written some books. Really interesting guy. He wrote a book called The Black Swan, and it's about kind of unlikely events that will sometimes occur and shatter the preconceived notions. And his book was a lot about the financial side of things, the strange financial things that can happen, like bubbles and crashes, and that kind of break our models. But one of the quotes in his book on this idea is that the minds of the gods cannot be read just by watching their deeds. And I think this is an important idea for science, for a lot of the applications of math that we're going to be talking about, whether it's moments and centers of mass that we'll talk about today, or probability theory that we might think of applying to the real world that we'll talk about in the supplement, or whether it's just general thing you take with you to your physics class or chemistry class or stats class or whatever it may be. That essentially our models, we construct them by taking in information from the outside world, looking for common threads in that information, extracting those common ideas, abstracting away from the details, and coming up with a model that we then hope to apply outside of the realms that we directly observed. Maybe we're guessing what happens in the future, or we're guessing what will happen in a slightly different circumstance on the basis of what we know happened in the past, or what happened in these other circumstances. And his argument is, of course, that's a very good and valuable thing to do, but maybe we should always be just a little bit humble and not think that we're actually writing the laws of physics, or that we're writing the laws of economics, or whatever it may be. Our models are always just you know, approximations of reality that range from, you know, pretty terrible to pretty good, but never perfect. Um, Isaac Newton has this kind of analogy where he has some quote about like a shiny pebble, and he kind of likens all of his work to, you know, walking along a beach and occasionally finding a shinier pebble than his shiniest pebble and being all excited about that. And meanwhile, there's kind of an ocean of truth that lies undiscovered. Um, Richard Feynman, the famous Nobel laureate physicist, you can look up if you want. There's a really good interview of him with I think it was just like a TV interview kind of guy that they sat down and did an hour long or 2 hours or something interview. And there's tons of really interesting little snippets from that interview. But one of them is his analogy of a chessboard where he's, you know, likening the process of scientific inquiry and discovery to, you know, watching gods play chess with one another. And you can watch like kind of a small corner of their chessboard, and you know, notice some things every once in a while, and you write down rules, and then but then something strange happens that you hadn't seen happen before, so you need to constantly adjust your rules. um, so we certainly shouldn't, you know, throw out science and say, oh, none of these models are perfect. uh, our models are often useful, but we also shouldn't go the other direction and say, you know, I've written down F equals ma, and that is now like the law of physics. You know, that's just my approximation of the law of physics. Okay, so today's plan is to discuss moments and centers of mass. Are there any questions on anything from last week, anything from the homework, or anything before we get started? All right, let me get my papers sorted out over here. There we go. Okay, so moments and centers of mass. So we're going to start with a 1D, one-dimensional, discrete system, and we'll try to work our way up to uh, one-dimensional continuous. And when we see probability, we'll see that's going to be an application of 1D continuous. And then in Calc 3, you'll actually talk about 2D and maybe even 3D continuous systems. So what's the idea of a center of mass? In a discrete system, let's consider that we have, and this probably is reminiscent of some high school kind of science work that you've done, or certainly if you've taken introductory physics, this should be reminiscent. Let's consider that we have a weightless rod that has some masses sitting on it. Let's say that we have mass M1 and mass M2. So this mass on the left has mass M1, on the right has mass M2. Let's suppose that this is at location on this rod X1. So we have maybe a 0 point, you know, somewhere over here, and this is, you know, 1 foot to the right of that arbitrary 0 point. And mass M2 has location X2. So we have two masses. And we usually think of these as point masses. So we're thinking that instead of, you know, an actual block, if we had an actual cube of weight sitting here, there would be like some of the mass is a little further to the left and some of the mass is a little further to the right, but we idealize these as point masses where all of the mass is sitting exactly at location X1. So two masses, M1 and M2 at locations X1 and X2 respectively. Now, if we consider a fulcrum, if we consider a point of support on this rod, and again, the rod is weightless, the thing they're sitting on is weightless, so it's only the masses that are affecting the torques and so on. Then actually, let me do something like this. If I consider a point of support below this rod, then I can see that each of these masses individually is going to tend to want to cause a rotation about this point of support. So M2 is going to want to cause a rotation this way. If M2 was the only influence that we had, the rod would rotate clockwise. And similarly, M1 is going to want to cause a rotation this way. If M1 was the only influence, this whole system would rotate counterclockwise. Relative to this point of support, I can think of a distance. We'll call this D1. The distance to mass 1. And D2. And maybe I'll just call this location X. So these masses, let's say each mass individually, comes along with a moment, a tendency to make the system want to rotate about a certain point, in this case, this point of support. So let's consider M1. The more mass that I have, or the more distance that I have, they both impact the moment in a linear fashion. So the moment is M1 times D1. And I'm going to call this capital M1. So sorry about that, but moments tend to get capital M and masses tend to get small m. I'll try to be careful to make the distinction obvious. And this is in the direction counterclockwise. M2 also imparts a moment on the system. It's M2D2. We'll call this moment 2, and it's in the clockwise direction. And these clockwise and counterclockwise statements are true as long as X, the point of support, is between X1 and X2, right? If X was like to the left of X1, then they'd both be wanting to make it go clockwise and vice versa. So I see it. I think it's kind of obvious here that M2, I mean, the block size, M2 is bigger than M1 and D2 is bigger than D1. So it's kind of obvious that my tendency to want to rotate to the right, my tendency to want to rotate clockwise is going to be large, and my tendency to want to rotate counterclockwise is going to be small. So net, this system is going to want to rotate clockwise towards the M2 direction, right? M2 is going to go down, M1 is going to go up, and it's going to rotate that way. I could rewrite these moments in terms of the X's. I didn't give myself quite enough room to do that. Let me try to move this down a little bit instead of trying to shimmy the X stuff in there. It's always a little bit of a gamble whether copying or moving things in OneNote is going to work nicely or whether it's going to like blow everything up. But thank God for Control Z. Whoever invented Control Z is like my best friend. Okay, so what's D1? And we're going to consider that X is between X1 and X2 here. So I think that's M1 times X minus X1. And what's D2? That's going to be M2 times x2 minus x. So at this point, my M2D2 is larger in magnitude than M1D1. That side kind of wins out. But for a center of mass, what I would like, let me just redraw this a little bit here. For a center of mass, I would like to put my base of support, my point of support, under a certain point. And I see if I move it over, what happens. Let me just erase most of this. If I move it over to the right side, what happens? Well, here I have a small distance d2 associated with a large mass m2. So I have a small times large. On the other side, I have a small m1 associated with a big d1. So I have a small times large. And I think that I can see that maybe I could find a location that balances these out, where these two moments, the tendency to want to rotate counterclockwise and the tendency to want to rotate clockwise, perfectly offset one another and the system stays balanced. I'm going through all of this. I mean, you might know the equation, from previous knowledge, but I'm going through all of this because just like our previous, how many examples in Calc 2, we kind of take a continuous problem, we break it down into the discrete problem, we solve the discrete problem and build back up to continuous. So we're going to do the same thing here in the 1D continuous. So it's important to, I think, to know this process of how we get to the formula at the end. But okay. So I see that I can choose a location, or at least suspect I can choose a location in between these two where I can make this offset perfect, where the small times large and the large times small are exactly the same. I'm going to choose to call this x bar. And I'm going to give that the name the center of mass. So now I can say, I can put an x bar there and an x bar there. That's the location of this base of support where my tendency to rotate counterclockwise and my tendency to rotate clockwise perfectly cancel each other out, and the system as a whole doesn't want to rotate either way. So I want to set moment 1 equal to moment 2, or in other words, mass 1 times x bar minus x1 equal mass 2 times x2 minus x bar. Or what do I end up with? I end up with m1 plus m2 x bar equals m1 x1 plus m2 x2. And then solving for x bar gives me x bar equals this. So this is my formula for center of mass in the 1D discrete case. As kind of a side note, why do I care about center of mass? Well, this is actually kind of why I care about center of mass. In other words, like, in a sense, my system as a whole acts as though, at least in some cases, and in some senses, acts as though I have all of my mass, m1 plus m2, the whole mass, the total mass of the system, located at the point, the center of mass. So in other words, if I had this weightless bar and I want to like push this mass forward, if I want to push this total system forward, just translate it in one direction. If I like push over here, then the system is going to kind of get pushed forward as a whole, but it's also going to rotate to the right. Oh, undid one too many. If I push here, the system as a whole is going to move forward, but it's going to rotate to the left. But if I push right here at X bar, the system will move forward, but also won't want to rotate, right? Or things like collisions or things like that. A lot of times you can take a complicated system and reduce it down to a point mass at a center of mass, and that can tell you a lot about the behavior of that system. Now, sometimes, sometimes that's irrelevant. If I want to know if this thing is moving along and if it's going to run into a wall over here, well, I can't just pretend all the mass is at the center of mass. But sometimes this is a very good tool to use. So in many senses, we can pretend that all of the mass is located at the location center of mass when we're doing certain types of calculations, instead of having to consider the contribution from each and every different component of the mass. Okay, so we got this formula. And this formula we can think of as the moment of the entire system over the mass of the entire system, the total moment, the total tendency of the system to rotate in one direction or the other over the total mass. That's another way that we can think about the center of mass is the moment of the system over the total mass of the system. So now what if I wanted to generalize this where I had n masses at n locations, m1 through mn, located at x1 through xn, where would xr be? Where would x bar be? It's just the sum of the individual moments over the sum of the individual masses. And we might be starting to get a little suspicious that we might have an integral, relationship here when we look at the continuous side of things. Okay. And just, I want to make one more thing clear from this relationship. Obviously, little m x bar equals big M. So again, kind of like I said, that the moment and the mass for the whole system relate to one another through x bar in a similar way that each of the individual moments and masses relate to one another through this distance. Okay. And what's a maybe typical application of that? So we could talk about, obviously not to scale, but a person standing on the earth, and you say, okay, this person or this block or whatever is under the influence of gravity, right? Well, what does gravity do? Gravity, roughly speaking, pulls two things together. Well, the earth is made up of 10 to the 50 or something little tiny particles. And each of those are pulling on whatever, all of the 10 to the 40 or something of your particles, do I really want to model every one of these interactions? Or do I want to say, well, I don't want to think about, no offense, but I don't want to think about you as a person in this situation. I want to think about you as a point mass. And I don't want to think about the Earth as this collection of tons of particles in this sense. I want to think about the Earth as a point mass. So whatever, you weigh 170 pounds and you're at this 3D point in space. So I just put a point mass at that location in space of 170 pounds, and the Earth weighs whatever the heck it weighs at some location, and it's here and you're there. And we just have these two particles pulling one another that have different masses at different locations. Much nicer to say model gravity like this than to say modeling it in some kind of crazy, particle by particle situation or whatever. And the other thing that I see that there's some nice symmetry. There's some nice symmetry here that I could use. If it was true that M1 equals M2, that the masses are equal, then for the moments to be equal, the distances have to be equal, right? Or in other words, if the masses were equal, what if M1 equals M2? Then I have M1 over M1 plus M2, but that's just M1 over 2M1. That's just 1/2. And likewise, the second bit, M2 over M1 plus M2 would also just be 1/2. Then X bar equals, not M1, X1. X1 plus X2 over 2. If my masses are equal on either side, or if later on, maybe if the density is constant, and if I have an axis of symmetry, if I can draw an axis between these two masses that splits them perfectly in two, then I can leverage this symmetry to say that that axis must occur directly in between the two. So if I have equal masses, or say maybe equal densities or something like that later on, then I can leverage symmetry. So I want to also keep an eye out for symmetry in these problems. Okay. So let's take a quick diversion then into 2D discrete. I'm going to go through this one maybe a little bit quickly, but it builds kind of directly on what we just talked about. So I'll go a little more quickly through this one. So here, let's think that we have kind of a weightless, 2D plane, or like a weightless plate that we're going to put masses on. And here I have two masses, M1 and M2. Mass 1 is at location X1, Y1, and M2 at X2, Y2. So I imagine that I have this kind of plate like this. I have mass M1 and mass M2, and I want to know where to put my cone under here to balance this plate with these two masses that could be different masses at two different locations. Well, there are two things that I want to balance here. If I put my fulcrum too far left or right, So if I consider X bar the X location of my balance point, or hopefully balance point, but if I put it too far left or right, if X bar is off, I'm going to tend to have a rotation, kind of in some sense, looking at it over here, like to the left or to the right. If I put it too far left, if I put the balance point too far left or right, the X arrow is going to tend to rotate about the Y axis. So I can have my is the moment about the Y axis. It's the tendency to rotate about the Y axis. If M1 was really large and M2 was fairly small, and my X1 and X2, like here, were roughly equal, if I put my balance point at 0, 0, my system would want to rotate in the direction I indicated here about the Y-axis. It would be a moment about the Y-axis. So the location of X bar, the X location of the balance point, is related to my, the moment about the Y-axis. And Y bar, likewise, is located or is associated with mx, the moment about the x-axis. I want to choose my vertical location of my balance point to try to stop rotation about the x-axis. So X bar is associated with my, the moment about the y-axis. That's what the location X bar is trying to eliminate, is the total moment about y. And Y bar, the Y location of the balance point, is trying to stop any desire to rotate about the x-axis. So Y bar is related to mx. I know it's a little bit strange that, it seems like they flip, but if we're thinking a moment about the axis is what this means, and this is trying to stop rotation about that axis. So I think, again, if we think back to first principles, it makes a little more sense. I'm not going to go through all of the details here, but X bar is going to be my over m, or it's going to be sum of mixi. The x distances of the masses are what is going to cause the system to want to rotate about the y-axis. So X bar is related to my, the y moment, the tendency to want to rotate about the y-axis. The tendency to want to rotate about the y-axis is related to the x coordinates. So this makes sense. But maybe why we call that my, the moment about the y-axis, seeing that interspersed in the x stuff might be a little confusing at first. But again, if we think about what those moments really are, it makes a little more sense. And then similarly, Y bar, mx over m, sum of mi yi over sum mi. So for a 2D discrete case, we have something pretty analogous. Okay, so now let's look at, in a sense, I suppose, 2D continuous. So we're going to think of a 2D plate or a 2D chunk of mass, but it's going to be defined by a one-dimensional function. So let's consider a 2D plate And we're going to start with a pretty simple, pretty straightforward setup. This plate is going to be given by the area under a curve above the x-axis in between x equals a and x equals b. So this plate has 3 flat sides and then 1 curvy side, f of x. And this is x, this is y. So here we're thinking of this being the kind of 2D plate. So you can imagine you had a hunk of steel or something, and you cut 3 of the sides flat like this, and then you cut this other side kind of curvy like this. And what I'd like to find is the location of the balance point for this plate. So if I wanted to take this plate of steel that's, maybe 1/4 inch thick or something, and I wanted to, in theory, like balance it perfectly on a little conical support thing, where should I put it on that cone so that it balances? Okay, so how can I think about this? I'm going to draw this again without so many dashes and so on. Well, thinking about this as a big problem, like kind of an overall attack, seems kind of difficult. But what have we done in the past? We've said, well, let me break this interval a to b into a bunch of little subintervals. Delta x, or a subinterval with delta x. If I take this little slice of this big hunk of metal, I have a curvy top. I have 3 straight sides. I mean, it doesn't seem like I've gotten anywhere, but delta x is small. This curvy top, as long as I don't have anything, too crazy, if I don't have a function that's like, discontinuous at infinitely many points or something crazy, as long as I don't have anything too crazy, I can approximate this by just a rectangle. This rectangle has, if this is location x, this is just a rectangle with height f of x. Let me move this over just a tad here. So if I just consider this ith box here with delta x is small, so we can approximate that top by just the flat side instead of a curvy piece, has height f of x. Well, I remember that I have a nice symmetry argument that I can make. If I can find an axis of symmetry, if I can find an axis about which my, in this case, 2-dimensional continuous structure is symmetric, then the center of mass has to lie on that axis. So what's the kind of center of mass here? And I think I forgot to mention, but the goal is to find the centroid, which is the name for a center of mass of a continuous thing like this. So where would that center of mass be? Well, I could say, well, this is left-right symmetric. the center of mass must lie on this axis here. It's also symmetric up and down across its midpoint here. My center of mass must be there. Again, by a symmetry argument. The center of mass has to be at height 1/2 f of x, 1/2 of the total height of that box. And it has to be at location delta x over 2 from the side. But like if this is basically location x, this is also basically location x, right? If we have a small delta x, we're not going to quibble over whether it's delta x versus delta x over 2, because all of those details are going to go away when we shrink delta x down. So the location of the center of mass of this block is basically going to be at location x, left to right, and it's basically going to be at height 1/2 f of x. So here I have a 2D shape that can be approximated by a rectangle, and that rectangle can be treated as though it is a point mass. We'll call it m sub I equals, I'm not really sure yet, but it's going to be a point mass of whatever its mass is at location x comma 1/2 f of x. What would its mass be? Well, its mass would be its two-dimensional area times its kind of like area-based density. So density per unit area. If I took a 1 by 1 unit punch out of this material and put it on a scale, what would that weigh? So it's kind of area density times its area. So f of x, delta x, times, we'll say rho, this is like an area density. So just some rho will also assume that we have constant density along this whole thing. So this isn't like a piece of steel that's like thicker on one end and thinner on the other end or something like that. So we're assuming this density is constant. Okay, so I have, again, what did I do? I had a big shape. I cut a little strip out of it that made a smaller, slightly wonky shape. But because it was very skinny, I can approximate that top curve as a top straight line. That makes a rectangle. I use symmetry to find the center of mass of that rectangle, and then I treat the contribution of this rectangle to the overall center of mass as though it were a point mass with mass rho f of x delta x at location x comma 1/2 of f of x. But I have I of these. I have one here and one there and one there and so on, right? So I have these are indexed by I have n of them. I now have n point masses. Of these masses located at these points. But if I have n point masses at certain xy coordinates, I can come back up to my algebraic structure and I know how to solve this. I know how to solve this in the discrete case. Can I solve this? Take delta x to 0, the number of slices to infinity, and then recover an integral. So what's my? It's the sum of mixi over m, sum of mi. And I should say this is approximate. So the masses times the x coordinates so I think I got everything there. Rho xi f of xi delta x, that looks good. Over sum of mi, which is sum of rho f of xi delta x. I note that the rows are going to cancel. So if I had a thicker sheet of metal or a thinner sheet, or if it was made of wood instead or plastic, the location of the balance point is going to be the same. It's just going to be more or less massive. It's going to weigh more or weigh less. What's y bar? And I got to be a little careful here. MIYI, this is YI. So what do I get? I get 1/2 rho f of xi squared delta x, then over the sum in the previous denominator, same thing. Now I limit, I let n go to infinity, delta x go to 0, my sums turn into integrals. And I see that sorry, I put my approximate equals in the wrong place. These are equals. These are the approximate equals. So my now equals the integral a to b of rho x f of x dx. And of course, if we wanted to, we see that this rho just comes out of the integral. This is the moment about the y-axis, whose contribution is from the x locations. We have mx, the moment about the x-axis. Again, the kind of one of the f of x components is from the mass. The other f of x is from the height. So it's the y location, the height, that's affecting the tendency to rotate about the x-axis. And then the mass in either of the denominators is just rho times the area. Then we have x bar. Again, seemingly strangely, but when we think about it, it makes sense. My over m, y bar equals mx over m. Any questions so far? Now let's take this one step further and investigate what happens if I have a top function f of x and a bottom function g of x. What is that going to change? Well, when I come over to here, when I take my little slice, it's going to go from G to F. The midpoint is going to be F plus G over 2. The midpoint in the vertical direction is going to be F plus G over 2. And the mass is going to be rho f of x minus g of x, the distance from the top to the bottom, delta x. So I have endpoint masses at location, or endpoint masses of rho f of xi minus g of xi, delta x, at locations xi, that's still the same, comma, well, here I get 1/2 f of xi plus g of xi. There's that, and that parentheses. I've got to be a little bit careful here. So here I have, so the two different places I used f here originally were for the height of this box as well as for the distance from the top to the bottom. So I've got to be a little careful. I used it both in the location of the center of mass as well as kind of in the area. So this MIXI, the XI is going to stay the same, but the mass is going to be F minus G. Same down here. Same here. And I maybe use a different color for this one. Where did this F squared come from? It came from MI times YI. It came from this times this. F minus G times F plus G gives me F squared minus G squared. And I can see how these are going to be exactly the same. The relationship of X bar and Y bar to the moments and the masses. But my mass is going to be rho integral A to B F of X minus G of X dx. Right. My my is going to be rho F minus G X delta X. moving into the integral, it's going to look like that. And then my mx, and here's this tricky 1/2 rho, my f squared becomes f squared minus g squared. Very non-obvious why that would pop out that way. It's from that multiplication and the difference of two squares formula. So if we had g of x being non-zero, these are the more general formulas, and we can see that we recover the formulas in black. If we just plug in g of x equals 0 everywhere, we obviously get the black formulas back, the simpler formulas. So again, we used so many components, the basic 1D and then 2D discrete cases. We used symmetry. We used our standard Calc 2 method of taking a continuous problem, chopping it up, approximating as discrete, solving the discrete problem, limiting to get back to continuous. We really built all of this up and really used a lot of these topics that you might have seen before, but also hopefully, even if maybe you've seen these formulas before, hopefully this at least gives you some context that maybe you haven't appreciated before. So then we don't really have time to go through an example today. So I'll bump that back to the supplement as well. So we'll do an example or two on moments and centers of mass, an example or maybe two examples on surface area, and then a little bit of a discussion on probability. So keep an eye out for those. I'll probably do one supplement on an example or two from this section, an example or two from surface area, and then probably a separate supplement on probability, just to keep them a little bit, keep them from getting too long. So keep an eye out for those coming up this week. Are there any questions on anything before we break for today?